Hello, AP Chem students, and welcome to topic 4.8, Introduction to Acid-Base Reactions. So the learning objective here is 4.8.a, identify species as Bronsted-Lowry acids, bases, and or conjugate acid-base pairs based on proton transfer involving those species. So we had an introduction to acid-base reactions in topic 4.7, but we're going to get into more specifics here. So you're probably most used to describing an acid as producing H plus ions in solution and a base producing OH minus ions in solution. But that definition, called the Arrhenius theory, is actually very limited because it only describes one kind of base and only situations in aqueous solutions. So you can see the particle diagrams that popped up here as I was saying those words. And so an acid, an Arrhenius acid, when you put it in water, fully dissociates into H plus ions and then the anion, whereas a base is composed of a cation and hydroxide, and then that also fully dissociates when put in water. The problem is that that is a very limited definition, particularly for the base. And there were substances that were recognized as acting as basic species that did not fit this definition. So two separate scientists identified the problem and independently proposed a new definition, which is now called the Bronsted-Lowry theory in their joint honor. So one thing I want to point out to you is that the Bronsted-Lowry, the Arrhenius theory, is not incorrect. It is just a much more limited theory than the Bronsted-Lowry theory. So if you look at this graphic down here, you can see the Arrhenius theory actually fits inside the Bronsted-Lowry theory. The Bronsted-Lowry theory, an acid definition doesn't change much at all, but the base definition does. So in Bronsted-Lowry theory, says that an acid is a proton donor and a base is a proton acceptor. And that fits many more situations, including describing ammonia as a base. So it's known that ammonia acted as a base, but the Arrhenius theory couldn't really describe the way that that worked. So the Bronsted-Lowry theory still considers acids and bases in aqueous solution, but incorporates the role that water plays. So if you look here, in the Bronsted-Lowry theory, an acid has an H plus still, that's the same as the Arrhenius theory, and that H plus transfers to the base. And so then you're left with a conjugate base and then a conjugate acid. And so then we can describe these conjugate acid-base pairs. So conjugate acid-base pair is that partnering that differs only in the transfer or only in that one proton. So here you have an acid and its conjugate base, and here you have a base and its conjugate acid. So this identifies conjugate acids and bases, which are the species that are the result of the transfer of the hydrogen ions between water and an acid or a base. So the other thing that's useful about a Bronsted-Lowry theory is then you can talk about the role that water itself plays in the acid-base properties. And so we're going to look at that here. So this theory handles the concept of weak acids and bases in a way that the original Arrhenius theory couldn't. And that's where water really comes in. So if you look at a strong acid, if we put a strong acid and we have it in water, because strong acids certainly are in water, it fully dissociates into the anion and hydronium, which is this H3O+, which is water that has had the hydrogen transferred to it. A weak acid, on the other hand, only partially does this. So you can see that if you're starting with this weak acid in water, some of it dissociates into the anion and hydronium, but not all of it. Now, if all other things in this situation are equal, you can see that this also impacts the pH. So the pH of strong acid is lower than the pH of a weak acid. That's not the focus of this topic, and so we'll talk about that much more in Unit 8. We can see the same situation with a strong base. Now, you'll notice with a strong base that actually we don't have to have water present to show this reaction, although generally it is. But a strong base dissociates fully into the cation and the hydroxide versus a weak base, which can act instead of needing the water, instead of producing the hydroxide on its own. Sometimes the weak base acts by pulling the hydrogen off of the water, and that's how the hydroxide is formed. So again, the role that water plays in the acid's base here. Okay. So we're going to look at an example below, and then we're going to label each species. And I'm going to talk to you a little bit more about the features of acids and bases here. So I've got two equations that we're going to look at. So this is acetic acid, which you know as vinegar. And then this is the structure of acetic acid. And so we're going to look at this atom in green here because that is one of the hydrogens. And so you can see that that hydrogen transfers to water, leaving behind this anion and then hydronium. So there we go. So you have C2H3O2 minus plus H3O plus. So this is the conjugate base because this is the acid and this is its conjugate base. The leftovers after that H plus is lost. Now in this reaction, your water then is acting as the base, and then your hydronium is the conjugate acid. It's the protonated form of the original base. So remember that the acid is the hydrogen donor and the base is the hydrogen acceptor. And so water in this situation acts as a base. Okay, so hydronium is the conjugate acid of water. It's called an amphoteric. Sorry, this is incorrect. Let me fix that really quick. Right, so hydronium is the conjugate acid of water. So now let's look at the second reaction here. So we have ammonia plus water. And so then let's just show what that can form. There we go. So here is a Lewis structure of ammonia and a Lewis structure of water. So in this case, one of the hydrogens from water is going to transfer to the ammonia. And so then let me move my face out of the way. And you can see that this is what is formed. So we end up with ammonium, which is NH4 plus, and then hydroxide. So again, this is how ammonia acts as a base. It removes one of the protons from water, leaving behind hydroxide. So then we have this NH4 plus and OH minus. So then this is the conjugate acid, and then hydroxide is the conjugate base. So the conjugate acid base pairs here, we have NH3 is acting as your base, and NH4 plus is your conjugate acid. And then you have H2O, water, acting as the acid, and then OH minus is your conjugate base. So then this brings up, this is where that word should have been, the amphoteric species. Water can act as both an acid or a base. And there are a number of amphoteric species. One of them is actually ammonia. There are situations in which you can actually remove one of the protons from ammonia and then be left with NH2 minus. But anyway, so that's how you identify conjugate acid base pairs and the conjugates just individually as well. Now, one thing that's important to note here is that with weak acids and weak bases, you can have this reaction turn around and go in the other direction. So this ammonium, can lose its hydrogen back to the hydroxide, reforming water and ammonia. And so that's called a reversible reaction, and that's going to become a very important topic in the course later on. Okay, so for now, you need to be able to recognize a few acids and bases as being strong, and then everything else is considered weak. So the strong acids and bases are those that are considered to fully dissociate, which we talked about before, and then weak acids and bases only dissociate to a partial extent. And so these are ones you need to have memorized, and this is on your memorization sheet. So we have 6 strong acids. So we have sulfuric, hydroiodic, hydrobromic, nitric, hydrochloric, and perchloric. So I want to point out the HI, HBr, HCl. That's all of the acids of the halogens with the exception of HF. HF is weak. But I put them in this order because there is a cute little memory aid. So I brought no clean clothes. Sulfuric, hydroiodic, hydrobromic, nitric, hydrochloric, and perchloric. And then the strong bases are easier to memorize because they're all hydroxides of group 1 and group 2. So that is it for this topic. So what should you be able to do with this? Well, you should be able to label the Bronsted-Lowry acid, the Bronsted-Lowry base, conjugate acid, and conjugate base in a reaction. You should be able to recognize that water is amphoteric and label it as either acting as an acid or acting as a base given the overall reaction or situation that you're examining. You should be able to list the strong acids and strong bases. You should be able to compare the relative strengths of acids and bases in a system by considering the dominant species after the reaction has been allowed to proceed, based on observations, data, or particle diagrams. So in other words, is it strong and we have fully dissociated, or is it weak and we have only partially dissociated? And then draw a particle diagram of a weak or strong acid and label the Bronsted-Lowry acid and base in the reactants and the conjugate acid and base in the products. That is it for this topic, and I will see you next time for oxidation reduction reactions.